Welcome to the world of turbulence modeling, right? And which obviously includes both the theoretical knowledge as well as the modeling component. So before I begin, my name is Vagish and I am a faculty or professor at Indian Institute of Technology Madras at the Department of Applied Mechanics and Biomedical Engineering in India. And in this course, we emphasize on both the theory as well as the modeling aspects of turbulence, because if you want to model turbulence, you must have a sound theoretical knowledge. The turbulence physics has to be taught first, and then we go into the modeling part. Before I begin, I would like to tell why should we even bother about studying turbulence, right? So why study turbulence modeling? Look around, most fluid flows are turbulent, right? All the practical flows that we see are turbulent. Be it in the industry or in nature. Like for example, the atmospheric and oceanic flows are turbulent, and even the human breathing, the moment we are alive here, all the biofluid mechanics, most of the flow turbulent. And when you go to industry, we have, you take it from aerodynamics to propulsion, combustion, all the applications will involve turbulent flows. And some example animations that I have put, these are in my research lab. And for example, you're looking into the flow over a bluff body, a bluff body aerodynamics on the left side, or it could be a liquid atomizing, say in a combustion chamber, right? Fuel getting atomized, or the liquid column breaking up into fragments. Or it could be the atmospheric boundary layers, where you have buildings and so on, like how does roughness induce turbulence and so on. So these are complex flows which involves turbulence. So there are many wide variety of applications to turbulent flows, and the physics itself is very interesting to study. And another reason why we study turbulence or turbulence modeling is experiments are difficult, expensive, and sometimes it's even impossible to do experiments. Okay, that does not mean that experiments are not needed. Both turbulence modeling and experiments, they complement each other, and we should take both together. But the fact that experiments are more expensive and many times very difficult to do it, and sometimes even impossible. For example, how do you even measure tomorrow's weather, right? I mean, if you want to predict the weather tomorrow, or if you want to know where does the cyclone go and land in a week time, or when does the monsoon arrive, all these things, these are predictions. So you cannot do measurements of tomorrow's or future weather, right? So this requires turbulence modeling. And it could be like, for example, on the left image, you have this particulate dispersion. That is like if you're interested in how does the pollutant dispersion move around in atmosphere, right? So it's very difficult to measure this in the lab, like simultaneously measure both the fluid velocity as well as the particle velocity, and these particles are inertial particles. Very tough to measure these two together simultaneously, and the CFD calculations are of course come much useful in this kind of problems. Or it could be like a combustion. It's very difficult to measure turbulence in a combustion problem, right? Simultaneous measurements of because you have a competition between turbulence and reactions and their interplay. So some of the problems are difficult to even measure. So in this aspect, the turbulence modeling plays a very vital role to understand both the turbulence physics as well as to solve engineering problems. So the prerequisites to take this course, the first thing is you must know postgraduate level fluid mechanics and some basic knowledge of computational fluid dynamics, or the CFD. This implies that you have a sound knowledge of Navier-Stokes equations, how it's derived and what is the physical meaning of the mathematical aspects of the equations, as well as you have a good knowledge of the numerical methods under the umbrella of CFD. Will help is essentially turbulence modeling is you can say an advanced CFD course. Some basic CFD knowledge is definitely useful. And coming to the audience, I welcome undergraduate students who are in the pre-final or final year. That means they would have studied some postgraduate level fluid mechanics and advanced fluid mechanics and basic CFD courses, right? And this is of course covered at the master's level, that is postgraduate students, both masters and doctoral students. This should have been taught, so they are also welcome. And also I welcome practicing engineers, scientists, or even faculty who are teaching CFD, so they're also welcome to take the course. And coming to the syllabus, this is just a compact version of it. It will be a lot extended. And so basically, as I said, theory must be first learned well. So a foundation will be given for turbulence theory in the beginning of the course, which includes like the statistical aspects of turbulence and the governing equations of both the mean fluid motion and the turbulent fluid motion, and also what do we mean by a turbulence closure problem. So if we look at turbulent boundary layers, what are the different aspects and how it is different from a laminar boundary layer, and so on. So all these theoretical aspects has to be known first before we go into model turbulence. And under modeling turbulence, there are two classes of turbulence models. The first is, of course, statistical models, which is basically, you can call it RANS models or Reynolds average Navier-Stokes models, and it has many variations like eddy viscosity models or the Reynolds stress models. And also, how do you incorporate the wall boundary conditions, whether you want to have wall functions or you want to resolve the wall all the way close to the wall, those kind of considerations will be taken into account. And also, it is known that this statistical based models have some deficiencies. These are known and there will be some error in their predictions, and so we look into how we can make or how we can improve these so-called RANS models using the realizability constraints. Okay. And then we move on to the second part of the course, which is on eddy resolved techniques. Eddy resolved techniques will essentially have direct numerical simulation at the one end of the spectrum. The other one is, of course, the large eddy simulation, and where we look into types of filters that we use and also the various subgrid scale models that can be used in an LES calculation. And also we'll briefly touch upon the hybrid models. The hybrid implies a mix of both RANS and LES, right? And how we can take advantage of these two class of models in an industrial flow. That will be touched upon at the end. And coming to the text and reference books, these are the 4 books that I can recommend. The Turbulent Flows by Stephen Pope, or the Introduction to CFD by Versteeg and Malasekara, or it could be if you're interested in second moment closure models or this Reynolds stress models, this Modeling Turbulence in Engineering and Environment is a book. And also Turbulence Modeling by David C. Wilcox, right? So these are the books I would recommend as reference books or textbooks. Whenever you take a course, you need to know what is the key outcome, right? What is the takeaway from this course at the end of the course? 3 things I would like to say is that at the end of the course, you will have strong fundamentals or theoretical knowledge behind turbulence models, like how the models are built and why it is built the way it is. And this includes both the statistical methods as well as the eddy resolved methods. And the another aspect is that you will gain the knowledge of both the advantages and also challenges involved while implementing a turbulence model in a computer program. That means, let's say you are a programmer and you already have a computer program, and you want to implement a new model to test, or you want to develop a new CFD code with a particular turbulence model. Those kind of aspects will also be gained in this course. Or if you are an engineer, you want to apply turbulence modeling in CFD calculations, then of course you will gain confidence assessing various turbulence models in both open source CFD codes as well as commercial CFD software. Finally, I would like to acknowledge my teachers. This is a verse in Sanskrit which essentially means that without the teacher we are nothing. The knowledge that I have gained and that I am disseminating in this course is essentially due to my teachers. Verse essentially means that we salute the teacher who creates, sustains and destroys the ignorance in us. So 3 teachers who are very special, with whom I learned this art of turbulence physics and modeling. I would like to thank Professor William K. George, Professor Lars Davidson and Professor Helge Andersen for all the knowledge that I gained when I was studying with them. Thank you, and I welcome to see you in the course.